And we've already gone over tests, right?
Yes.
Okay. All right, so anybody have any questions on what we did yesterday? I want to do one problem just to make sure, because I don't think I did it yesterday in here. And I want to emphasize to you, when you are converting from a polar equation, all right, from a polar equation to a rectangular equation, if you don't follow my rules, sometimes your ending equation is a disaster. It's technically not wrong, but it's a disaster. And if you ever run into a multiple choice question or something like that at a state tournament test, you're not going to see your answer there. So let me give you a couple of guidelines in the event you get some uglier looking problems. So I'm going to, here. So for instance, what if I gave you this polar equation, and this would be about as ugly as they could get it. Okay, so I give you something like this and I say, and clearly it's a polar equation right now because it's got r's and thetas, right? Who knows what this will look like? My guess is some kind of maybe ellipse or hyperbola. Who knows? We'll have to see. Okay, not that that would be only from experience. It's not like I'm like, oh yeah, elliptical. I mean, I really have just done a bunch of these and kind of see the trend that happens. Now, first thing I'm going to give you a hint with is when you're simplifying and converting, always get rid of fractions. So clearly I have a fraction right now. So what could I do to eliminate that problem? I could cross multiply and I wouldn't have a fraction anymore. So at any point in the problem, like even if I replace sine, for instance, with y over r, because that's what sine of theta is, it's y over r. When I do that, I literally inserting a fraction into the problem will then cross multiply and eliminate it. So constantly think about eliminating fractions as you're doing that, and your life will be significantly better. Okay? Okay, so right here, I see a fraction. Oh, don't really like that. So r times this, and 1 times 3. Okay, great. I eliminated fractions. I feel a little bit better. All right? Because remember, this whole r equals form, that's just a form that your calculator uses. We're going to be doing a lot of those forms today where we have r equals. So that's just, it's like having y equals. It's not any better. It's just the way you would present it in your calculator if you wanted to try to graph it with your calculator. So nothing overly special about this. This is just as much of a polar equation as that is. Okay? So in the process of converting now, what do I need to get rid of? The r's and technically the thetas, but since sine is with that theta, why not, right? So right here, I need to get rid of those three things. So I like getting rid of replacing trig functions first, okay? Now there are people that come in there and say, well, Mr. Hurry, you told me that r squared was that, so that r is this. So why wouldn't I just replace the r's also? And the short answer to that is because I don't want you to. The long answer is because it makes your life get messier and messier and messier unnecessarily. So go ahead and replace the trig functions with their values, what they're equal to. So what is sine equal to in trig language? It's not y, that's the unit. We got to get sloppy and we say sine is the y value, cosine is the x value, but we're not dealing with a unit circle. We're dealing with any angle of any radius or any length. So y over r, you with me? Okay, so I come in here and I put 2r plus 5r times y over r. And by the way, if you're thinking to yourself, you know, yesterday you told me that x equals r cosine theta and y equals r sine theta. If you happen to remember that and you want to replace the whole r sine theta with y, great, because look, that's what ends up happening anyway. You're just left with the y there. Are y'all seeing that? Okay, now I'm down to here. 2r plus 5y equals 3. Or am I in rectangular form yet? Okay, so I have one more thing to worry about, and that's that r value. Now at this point, I've gotten rid of fractions. I've replaced the trig functions. Notice I got rid of fractions again with some process. If that r didn't cancel right there, then I would have multiplied through by that r to get rid of that r as well. I'm constantly trying to get rid of fractions. And then the last thing is replace, when I say trig functions, I'm really talking about trig functions and their thetas, okay? And then I want to replace r's replace r with its equivalent, x squared plus y squared. And in a perfect world, it would be r squared, and I would replace it with just x squared plus y squared because that's pretty. So the last step I would have in this problem would be to do this. And at this point, is it rectangular? Has to be because there's no r's and thetas. Now, the last curveball I'm going to throw you is I'm going to ask you on all of the problems that you answer to leave your answers like this. To leave them in ax squared, by squared, cx plus dy plus e equals 0 form. Which means if your answer is really simple, like if you end up with something like r equals 10, if you end up with something like x equal 10 is your final answer, then in this form, it would be 1x, subtract the 10 over, you'd leave it like that. If you end up with something like x squared minus y squared plus 3x equals 4, in this form, you'd leave it as x squared minus y squared plus 3x, subtract the 4 over. You don't have to leave those spaces. Are you with me? But you would leave it that set equal to 0 form. Is this in that form right now? Not with that square root, it's not. So what do I got to do to clean that up so that it would be in this form? They said move the 5y over. What is your goal in that? So moving it over gives me this. And then I could square both sides. And I really don't have to move the 2 over as long as you remember to do what? Square both. So 4, square root goes away. Of course, you got to square that, right? You can't just square each part. Remember how to square a binomial? Square that times 2. And then the last step would be to what? Just clean that bad boy up. So you're going to have a 4x squared. I'm going to try to save a line of work. You're going to have a positive 4y squared, but then what are you going to do? Subtract that 25, which is going to leave you with negative 21y squared. Then you're going to add that 30y and subtract that 9 and set it equal to 0 so that you can have it in that form. Do you see that? And can you look at that right now and tell me what that is? What is it when you have both terms squared, but plus minus? It's got to be a hyperbola. It would be a circle if you have what? Both terms squared, both positive, same coefficient. It would be an ellipse if you had both squared, both positive, or actually both negative, but both positive typically, and different numbers right there. But if it's plus minus, it's going to be a hyperbola. Unless it's some degenerate. But again, I'm not going to make you put it in hyperbolic form. It's not a conic sections test. But I am going to ask, this is probably the hardest one I give. So if you're looking at that and going, I'm down with that, then you're going to be fine. But there is some algebra involved to go from here to there. It's probably worth a couple points. Y'all with me? And I have never given a test that didn't have a question similar to that on there. Never have. Okay? For those note takers out there, or mental note takers. Yes, nothing leaves there. Are y'all with me? But guys, let me just tell you, if you don't constantly start getting rid of fractions, it starts getting nasty. Like right here, if you replace sine with y over r in here, now you got fractions inside of fractions. I mean, this is what I see people do, and they just get lost in the algebra. They go, oh yeah, r is square root of x squared plus y squared. Sine is y over r. Oh yeah, r is x squared plus y squared. Ugh, I don't know what to do. Now, technically, that is in polar form, I mean, rectangular form. You got rid of your r's and thetas, but that is not the form. And most people at this point, they're like, I don't even know what to do. So if you follow my rules in terms of get rid of fractions whenever you see them or whenever you create them, replace trig functions and their thetas first, right? Or trig function or the theta, whatever comes, or both, and then replace the r's last, because a lot of times they cancel out nicely and you don't have to deal with them. But if you do that in that order, constantly getting rid of fractions as you go, your answers are you're gonna find that you have a lot more success with these. It's a lot more simple a process. You with me? Okay, here's what I want to do today. So today I want to introduce you to some, and tomorrow, well, and Monday, I want to introduce you to some polar graphs that are common to, I say common, they're not that common, but they have special names like Limacon, lemniscate, cardioid, you know, all these funny little graphs. We're going to be talking about them, rose curves. So what I want to do, you're going to have to be able to graph these on your own. But I want to show you how your calculator creates them and see if you can start noticing some patterns. Because if you notice the patterns, this becomes really simple. And you don't need your calculator. And you won't have your calculator on the test for this. Okay? So I want you to go to page, I think it's 43. All right, so go to page 43. And I want you to take your calculator just for now. And I want you to set up your window. All right, so turn it on first. Did we put it in, did y'all put it in polar mode yesterday? If you have it in polar mode, great. If you do not, remember to do that. Go to menu. Here we go. Go to, do this. So if you're not in polar mode, hit the menu button right there. And then go to graph entry, which is 3, and then go down to polar, which is 5, and it will put it in polar form. And then what I want you to do, okay, then what I'll,
make sure y'all have ratings.
Then what I want you to do is make sure that either one of two things. In fact, you can go to degrees. In fact, go to degrees, but do this before, like right here, on my R1 right here, I'm going to make my theta go from 0 to 360. And I'm going to make my theta step, not 0.13, I'll be here forever. I'm going to make my theta step, let's just make it a cool 5. Now what this is going to do, it's going to plot points every 5 degrees from 0 to 360. So it's going to plot 72 points on this graph and connect the dots. That's probably fine. If I make my theta step 0.1, it's going to graph 3,600 points, which is going to take the calculator a little bit longer. Now, your calculator is so good at this point. Actually, yours is so good, I could even make it a 1. You'll see the difference in how quickly it graphs it. All right? So 0 to 361, and then change that rad to degrees. And I'll be totally honest with you, that should be fine. You should be able to leave it on this if you do that. And notice on my setup, I did not say to do that, but whatever. We're going to do this, and we're going to change your settings to degree. Oh, that's different. I don't want that. I want menu 8. So go to menu 8. Not the gear doesn't do the graph. So hit menu 8 for settings, and those are the graph settings. And go down there and change that to degree. Do y'all see the difference? Yes? The settings for this graph, the settings for the graph are not the gear. You can't just click up here and change that to degrees and fix the graph. That only fixes your calculation screen. Y'all seeing that? Okay, so now right here, when you hit tab, you should see R1, 0. I'm going to change that to 360. I'm not exactly sure why it's. I think once you actually enter an equation in, it won't. But if I'm wrong, we'll just have to stick with radians, and I'll have wasted our time. Okay, so here we go. Here's the first one I want to graph. If you look at number 1 on your page, 43, I think it is, it says 2 plus 3 cosine theta. So I'm going to enter 2 plus 3 trig cosine, and remember your theta is in the pi button. So if you click on pi and go to the right, you get a theta. And when I hit enter here, you'll notice that I don't see much of my graph because my window's bad. So I'm going to go to my window, back to menu. And before I move, I got to make sure everybody's in the right place. And I'm going to hit 4 for window, 1 for window settings. And I'm going to change my settings from, actually, you know what? There's a button for this. Go menu, window, and hit standard, number 5. Does everybody see their screen kind of like this? Okay, if you don't, we need to fix this now. So, okay, you just have the wrong thing back there. So on tab, you're close. You're supposed to have 2 plus 3. 3 cosine.
Oh, there it goes.
Does everybody else have this? Does everybody's window look okay?
How do you,
I need to get you right. Good. Yeah, so you're not in, you're still in function mode. So you want to be in menu, graph entry, poll.
I feel like you're doing.
Now that you're poll, you can type that. But change your step from 0 to 316.
Being a person not cool.
After you type it. Anybody else not in the right place right here?
It's not a place.
Corey did yell at us.
how do you,
Like, y'all should be more patient.
Okay, so
If you're like, we're
0
not the
to
one.
360.
You were making her.
You already changed it to degrees. And
What's
take a
the
step. Anybody else?
like,
It says it on this little piece of paper right there.
Yeah, I kept trying.
Oh. Yes, you did, didn't you?
That's why we're watching that movie.
I'm sorry.
Hmm?
I'm sorry.
You're watching the movie.
Okay, so it's
I'm
on this
sorry.
level. 1.
I liked that line.
You want to keep on R1 or you're going to have all kinds of
We
graphs.
got invested in that.
We did, and you have a couch. Wonder if people are allowed to see it now.
So we're on R1, there you go. Anybody else?
I'm good.
Everybody good? Nobody's lying to me? Okay, now again, I'm only doing this at the very beginning so you see some patterns. And then once we establish the patterns and how to kind of sketch these graphs, we're going to be good. Now, I also realize that, again, we've talked about this before, some of you are artistically impaired. So what we're going to be doing here is figuring out how these numbers right here, I'm going to go and grab this equation and slide it up here. We're going to figure out what this 2 and the 3, what the 2 and the 3 and the plus and the cosine are doing to this graph. Because if I change that plus to a minus, or I change that cosine to a sine, this graph starts going in different directions. So let's just kind of, and what you're going to be doing is plotting enough points to be able to graph this thing. Now, this particular graph is called a Limacon.
Ooh, it's French.
Limacon, or Limacon, like is what I'd rather say, with an inner loop. So this is a Limacon with an inner loop if you want to speak English. It's a Limacon with an inner loop. If you'd like to go the French route, it's up to you. Whatever makes you feel good. Okay? And I think that's how you pronounce it. Anybody in French here? Close?
Yeah.
Limacon? Limacon. Okay. And that, if you want to know how to make that C with a little funny thing on the bottom, I always see it as a C with a 5 on the bottom. Really, that's what it looks like to me. So it looks like a 5 without the top part just joined on there. But Limacon with an inner loop. Now, if it doesn't have that little loop on the inside, it has a different name. Okay, but so I'm going to talk about the points that we need to figure out. We're going to be graphing the point where the loop begins, the tip of the point, and we're going to be crossing the 2 places right here and that place out here. Now remember, even though your calculator says X and Y, there are no X and Y axes on a polar graph. There are no x and y axes in this equation. So your calculator doesn't know how to get rid of those even in polar mode. But they don't look at those and go, oh yeah, that's the 0.5. Now it is the 0.50, but not because you went 5 over and 0 up. It's because you went 5 towards 0 degrees. Okay? This is not the 0.02. This is 2 at 90 degrees. Are y'all seeing that? This is not the 0.00. This might be 0 at 275 degrees. I don't know. We'll play with all that. But I want to figure out some relationships here. Now, what is this length right here? This total distance I went out. 5? Where do you think that 5 came from? To me, it looks like the 2 and the 3. Now, if you really think about r, what r is the distance away from the pole, right? What is the biggest possible value that cosine can be? The biggest value you can get from cosine? 1. Smallest is -1. And when is cosine its absolute biggest? When is cosine 1? At 180, it's -1. At 0, it's 1. So doesn't it make sense if cosine is its biggest value, which is 1, then 2 plus 3 times 1 would be 5 at 0 degrees? There you go. Are you with me? Now, where would cosine be its smallest value? -1 at 180, right? Are y'all with me on this? So if cosine was equal to -1 at 180, what would that give me? 2 plus 3 times a -1? -1. So at 180 degrees, what do? I go back -1. Are y'all seeing this? Now, when is cosine equal to 0? At 90, straight up at 0, and 270? So if cosine was equal to 0, then what's the r value? 2. And notice at 90 and at 270, I'm up 2. Or I'm out 2. Are you seeing this? So what I have started to notice is that on cosine graphs right here, on cosine graphs, because it's maximizing in a certain direction, and cosine is maximum value at 0, I notice, or possibly, and you'll see in a second, at 270, because its absolute value is maximized. Whenever I have a cosine right here, the graph is going to be pushing left or right. But look what happens when I change it to a sine. When I change it to a sine curve, check it out. It pushes up. Now, why would it push up? Because where is sine maximized? At 90. And at sine of 90, what is sine equal to? 1. And what's 2 plus 3 times 1? 5. So the biggest r could possibly be is when the sine value is equal to 1, and that occurs at 90. Well, I've noticed sine pushes up towards 90. Now, if you're wondering, well, you said up or down, or left or right. Well, check out this. What if I change it back to cosine, but I make that a negative? Now think about this for a second. When would r have its biggest possible value? If cosine was equal to -1, that would give me 2 minus 3 times the -1, which is 2 plus 3. Isn't that the biggest it could possibly be? So where is cosine going to be maximized? I mean, where would the r be maximized? When that was -1, which would be at 180. So which way do you think this thing goes?
That way.
Must go this way, because that's where the maximum distance out would be, and you'll see, bam, going that way. So from this right here, you should see that right here, the cosine and the trig function and the negative or the positive determine direction. So when you see positive cosine, which way? Negative cosine? Positive sine? Negative sine. And what is that maximum value?
1.
What is that maximum distance out? Whatever those two numbers are added together, the absolute value of, we call that the A and the B value. So when you see R equals A plus or minus B, and it's either going to be sine or cosine, if you take the absolute value of that A right there, the absolute value of that B, just ignore the signs and add them together, that's the max, the maximum distance away from the pole. And that's kind of the direction the graph is going. Are y'all seeing this? Now,
What does tangent do?
we're not even going to look at the tangents on these, but it makes it obviously a totally different kind of graph. Now, another thing I want you to notice is, when would it be minimized? What's the smallest possible value you can get out of, say, an equation like this? Think about smallest possible value of R. Wouldn't it be where cosine is a 1? Because then I would be subtracting the most. Does that make sense? I'd be going 2 minus 3 if cosine's 1. If cosine's a half, I'm not subtracting 3, I'm only subtracting 1.5. If cosine's 0, I'm not subtracting anything. So the smallest, the most negative it can be would be when the cosine is 1. Well, that length right there is the length of my loop. So if I ever look up here and I see that 2 right there out front, if I take that and subtract it from the other value, again, ignore the signs. If I do that, so if 2 minus 3, if that gives me a negative number, that's the loop length. Does that make sense? Because that's where I'm going back negative inside. So there's my loop length. And right here it's 2, not because it's a minus 3, it could be 2 plus 3, 2 minus 3, but because I went that minus that and got a negative, that 1 right there, that value I got tells me to go back in a negative 1. But that's just, if you take the absolute value of that, that's my loop length. Okay? Now, this number right here, that up 2, down 2, that's always the lead number. So whatever it starts, why? Because is there a chance cosine is 0? And if cosine of theta is 0, then all of that goes away and your radius has a length of 2. And it just so happens cosine will have a length of 0. If it's going left, it has a length of 0 there and there. If it's going right, it has a length of 0 there and there, this part. If it's going up, you would mark it this way. So let me just change the numbers on you. Look at the second one that I asked you to graph there. I'm going to graph 2 plus 4 sine. So 2 plus 4 sine of theta. By the way, can you eyeball this right now and tell me where you think it's going based on what we've just learned? Positive sign going up. How far up? 6, because that's as big as it could possibly be. And it would make sense that if it's going up, that it's maximized that way. So 2 plus 4 is 6. 1, 2, 3, 4, 5, 6. What's the length of your loop? 2. Look at the length of it, because 2 minus 4 is a negative. So the loop exists because it's a negative value, but it'd be 2 on the inside of the problem. So that's a length of 2. So I can go, all right, and the loop is going to go to like right here. And if that lead number is 2, what does that tell me? It's going either way, 2. So I can mark these. And by the way, can R equal 0? Is it possible for R to equal 0? For R to equal 0, right here, is it possible sine, for instance, is equal to a negative 1/2? Sure, because sine can be anything from negative 1 to 1, right? And if sine were a negative 1/2, wouldn't that give me 2 minus 2 is 0? Right? So it's totally possible to have a point at the pole at 0. And if I have those 5 points, I can sketch this graph. Now, it may not be pretty, but I've got a loop. I usually start with the loop. And then it's crossing here and then coming back here. So, and crossing here and coming back here. and then this part has to come back and hit here. You all with me? Now I'm just going to guesstimate. I know a lot of people are going to end up drawing this. And that is a weird looking Limacons inner loop, but I'll take it. But more likely, it's going to look something like this. It's going to be pretty wide looking. But I only know this from experience. It's going to be pretty much like that. Are y'all with me?
What do you do? What do you
And
do?
that is a Limacon with inner loop. Do I?
What do you do when the loop length is 0?
We have a new graph. Let's move to the next section. So on your next section, and I couldn't have queued that question up. I'd ask, but where's my cursor? Okay, so this first set, I asked you some questions, but these questions are basically, we've already kind of answered them. All right? So right here, this first group are Limacons with inner loops. Not a loopy Limacon or anything. Limacon with an inner loop. If I ask you the question on the test, which I will. Okay? When I used to teach regular pre-cal, I would never write the actual word out. I would just say it. And it would be in the notes or whatever. And then on the test, I would ask them what the names of these are, just to have fun to see how bad they would butcher the spellings. And over the years, I've kept, now you guys actually do a pretty good job of it. It's not really that fun. But I've kept a list of all the bad misspellings over the years. And they're really pretty funny. When we go over the test at the end, I'll read it to you. I mean, they're really bad. It's kind of like, remember asymptotes? Astropoles? Like, they're right up there with astropoles. There's some really good ones. I mean, they're really pretty funny. I could just see the person going, dang it, and then just making crap up. But anyway. All right, so let's look at the next group. All right. The next group of graphs, the loop goes away, but you can tell that based on your rules. So check these out. These are actually called cardioids. Yeah. We actually one day, like, we were going over this and it landed on a Valentine's Day. So let me pick one. I'll tell you what, I'll change number 1. Let's make number 1 right here. Let's make it, is that 6? Let's go 3 minus 3 sine theta. Now let's see if we can sketch this based on what we already know from cardioids. Which direction do you think it's going to go? Down, because negative sine of theta. How far down? The total there, 6. Now if you're looking at that and going, why would you do that? 3 minus 3 is 0. It's because if sine was negative 1, it would be 3 plus 3. And where would sine be negative 1? 270. So at 270. But that's what we've already figured out, right? So you just add the two numbers up, you get 6, mark that straight down. That's the furthest this graph ever gets from the pole. It's like its maximum R value would be 6. Now, if I'm going down 6, how much do I go left or right?
3.
Lead number 3. And we said the length of the pole you got by taking the absolute value of the A and subtracting the absolute value of the B. And whatever I got, I make that positive, and that's the length of my length of my loop. What's the length of my loop?
0.
Which means I don't have a loop. But do I still go through the pole?
Yes.
Why? Because it's totally possible to have an R value of 0, isn't it? Yeah, if sine of theta is 1, which it is at 90 degrees, then at 90 degrees, 3 minus 3 times 1 would be 0. So at 90 degrees, I'm at 0. Now, I don't have a loop to deal with, so instead of drawing my loop, I just start with this part and go, well, I guess it bounces right there. It doesn't have a loop, the loop's 0, so it just kind of does that, and then it comes on around and makes a cardioid, hence cardiac heart. Happy Valentine's Day. So if we had this and we were graphing it, granted, you've already done the heavy lifting on this, but if I had that typed in, 3 minus 3 sine theta 3 minus 3, you can see that we have a heart right there. You with me? Now I realize yours will probably look like this. A lot. Again, I'm not quibbling. Really, the only way you'd be able to, unless you have an idea about what these look like, the only way you're really going to get a decent looking one is to plot more points. And to plot more points, you'd have to go, all right, what happens at, say, 240 degrees? Well, I plug 240 in. And you'd have to go, all right, what's sine of 240? Well, sine of 240 is down here. That's a what? Negative square root of 3 over 2. And if I've got two negatives, that's a positive. And that right there, what's root 3? About a 1.7. Divided by 2 is about a 0.86. What's 3 times a 0.86? I don't know, about a 2.4. 2.4 plus 3 is about a 5.4. So at 240 degrees, I'm going to go 1, 2, 3, 4, 5. Ooh, nice. 5.4. And I literally would have to plot points like that all day. I have no need for you to do that. I'm going to assume that if you had to plot polar points, you could, right? But I don't need you to do that. I just need either those 4 or those 5 if there's a loop. Right? And by the way, it's not a cardioid. For some reason, people love to write cardioids. Cardioid. All right? Are you with me so far? Now, what do you think happens if I change this from 3, I'm doing the next one, to 4? I tell you what, I'm doing the first one. What if I change that to 2 minus 2 cosine? All right, let's go 2 plus. 2 plus 2 cosine of theta. Does that make sense? Think about it, 2 plus 2. So if I'm starting 2 plus 2, if it's positive cosine, I'm heading to the right. How far to the right? 1, 2, 3, 4 to the right. What does the lead number tell me? Up and down 2. Is it possible for the R value to be 0? Sure it is. If cosine's a -1, 2 plus 2 times a -1 would be 0. So I can totally mark that. What's the length of your loop on the inside? 2 minus 2 is 0, right? And 2 minus 2 is 0. It would definitely give me an R value of 0. And I have an idea, and I bump, and do this. And by the way, when you hit the pole, I call it a, when you hit the pole right there, make sure it looks like a dip. Okay? Basically, think of it like you're pulling into a parking space and then backing out the other side. It actually dips. It does not do this. It does not come in here and curve through there. Okay? They don't do that. If it hits the pole, it's always a dip. Because remember, it's like a inner loop, right? So, but just without the inner loop. So it kind of bounces off that and comes back. Y'all seeing that? Okay, look at the next group. So those are cardioids. They are in the Limacon or Limacon family as well. The next group, and I know we're running out of time. I'm totally not worried about it. We will finish this up on Monday. All right, the next group, these are called Dimpled Limacons. Okay? So dimpled. But the rules still hold, but there's a slight twist. Now, look at this value right here. Again, what is the biggest value cosine can be, or sine? 1. So right here, if the biggest cosine can be is 1, what's the smallest r can be? That means it can't hit the pole. So if it can't hit the pole, instead of hitting the pole or having a loop, I'm actually backed off from the pole. But the rest of the rules hold. So check it out. Right here, I would look at this and go negative cosine. So which way am I going?
I have photos for semester James.
Awesome. Thank you very much.
Can you write the name of this one?
What's that one? Okay.
Oh, wait. Got it.
All right, so these are called
It's just dimple.
dimpled Limacons. All right. Now, these, again, negative cosine means what? Heading left. How far left? 5 and 3, which is 8, which means I'm off my curve here, but that's okay. Here, I'm here at 8. Everybody with me so far? How much up and down?
5.
Lead number, 5. Now, here where we go. If I took the 5 and subtracted the 3 and got a negative number, what does that tell me? Length of my loop on the inside. If I take that number and subtract that number and get a 0, that means no loop and I have a cardioid. But if I take the lead number and subtract that number and get a positive number, then that means it's a dimpled limacon, which means instead of hitting the pole or going on the inside, I go back the other way that amount. Are y'all seeing that? And then instead of dipping there, I dimple there. Instead of dipping, I have like a little curve, but the curve occurs back away from the pole that amount. So I put like a little parenthesis in there to show like a little dimple, and then I just curve it back around, and then come all the way back over here for the dimple. Y'all seeing it? I got no time. Hey, study what you've learned. Make sure you can do what we've learned. And then I don't even think I have a homework assignment today. And then we'll come up and finish this up hopefully on Monday. Y'all have a great weekend.
Sorry.